This section will introduce a fundamental reinforcement learning concept, temporal difference methods. We'll progress from basic TD implementations to implementing them in a revolutionary deep RL algorithm called deep Q networks. Let's start by exploring TD methods. TD methods are a way of creating and updating state value estimates. They update a guess towards a guess. They learn directly from episodes of experience. TD methods are model-free. No knowledge of the MDP model's transitions or rewards is needed. They can learn from incomplete episodes by bootstrapping. We'll go over 4 TD methods this section: TD learning, SARSA, SARS, and Q learning. This video will discuss TD learning. Let's try to visualize what TD learning is. The image on this slide shows an example of estimating how long it takes to get home. The red arrows show changes in the estimate as new information, i.e., the weather or amount of traffic, is received. Using TD learning, we are updating our guess at arriving home. At each step, we shape our estimate using the next estimate. This is TD0 or one-step returns. In TD methods, we bootstrap the estimates mid-episode. In TD learning, we don't need to wait until the end of the episode to update our estimates. We can do so at each step. As we gain more information, we update those estimates with that new information. Next, we'll go over the TD formula before showing some pseudocode and implementing TD learning in Python. TD0 is the one-step update of TD learning. The TD learning updates the current state value estimate using the reward and next state value estimate. The TD error and TD target are convenient terms to know when comparing TD methods and how the update is done. Some algorithms use the TD error and TD targets instead of the complete formula when performing updates. We'll implement this pseudocode in our TD0 example. Each time step, the agent will bootstrap its state estimates using the TD formula. We'll show TD learning in code using the grid world environment. Let's render a few frames of the grid world environment. The grid world environment is a simple 4x4 2D environment. The agent is represented by X and tries to reach the upper left corner or lower right corner, T. If the agent reaches either corner, it receives a large reward. Now we're going to use TD learning to estimate the state values of the grid world environment. And then each time step in the environment, we're going to use the m.step with that random policy. Here's where the TD0 formula comes in. So the current estimate of the state value array in the current state, we update that by the last held value plus what we use for the TD formula. And so the update, as we saw in the formula, it's the learning rate alpha times the reward, gone from the m.step, plus the discount factor gamma times the estimate of the next state from the next state value array, minus the estimate of the current state. Then we do this for every time step within the episode. If the episode is done, we reset. And if the episode is continuing, we set the current state equal to the next state. And we return the state value array. All right, now let's run that TD learning formula. So we're going to return some state values. The TD learning value estimate initialize those state values to 0 and then uses the TD0 formula that we went over to come up with the estimated state values. Before we finish this video, there are 2 key concepts in RL related to TD learning: n-step updates and model-based versus model-free. N-step updates allow multi-step returns and bootstrapping over multiple steps. The TD target can look n steps into the future. We'll discuss this further in section 4. One classification of RL algorithms is model-free versus model-based. In model-based methods, the model is given, like in the dynamic programming taxi and frozen lake examples, where the model is learned. A model is anything the agent can use to predict the environment. The agent then uses the model to plan future actions. Model-based methods are generally more efficient, but can suffer from model estimation errors, which cause inferior performance. In model-free, no knowledge of the underlying MDP is given. The agent uses trial and error to learn. Model-free methods require more data, but generally outperform model-based methods when the model is learned. TD methods are model-free. Many model-based methods use model-free learning as part of the algorithm, so it isn't always a clear distinction between model-free and model-based. An open problem in RL is how to harness the efficiency of models while getting the superior results of model-free methods.